is parametric surfaces and their areas. So typically, to get a parametric surface, you describe it using two variables u and v, and then you have an x component, a y component, and a z component. Okay, and this typically is going to define a surface. So one example, I've put a few examples here. This one right here is going to be this is going to be a plane. And the plane is going to go through the point R0, through this point right here. And then the vectors A and B. So A and B, these are boldface, so those are vectors. Are non-parallel vectors in the plane. Okay. So any two vectors that are not parallel, but are vectors in the plane, and then any point in the plane, and then this will be a parameterization for the plane, the surface that is the plane. Okay, so that's one example. Okay, the second one, what do you think this one is? Now, this could also be written as theta, comma, r. So the u and the v is not necessarily wait a minute, r, maybe something else. Maybe not an r, maybe instead of an r, maybe I should put a z. So a cosine theta, a sine theta, z. Okay, so any idea what this is? And let's say a is some positive number. So a is positive number. This looks like cylindrical coordinates, right? Except this a has been replaced, except the r has been replaced with an a, right? So this is a cylinder with radius a. And so just to give you an idea what it looks like. It's going to look like this. So the center of the cylinder is the z-axis, and it goes infinitely in both directions. Now, also with these parametric equations, of course, it's not just going to be this usually, although it can be. And you can say u and v goes from you could say u and v goes from negative infinity to infinity. Okay, but probably you wouldn't make u do that. You'd probably make u go from 0 to 2 pi. Okay, that would go all the way around the circle. And then if you did if you said, let's let v go from 0 to 4, for example, then this would be just this part of the cylinder. It's going from 0 to 4. But you could also make it go from negative infinity to infinity. Okay, so again, there's parameterizations that you put on it as well. Okay, this last one, this is where you have, if you have z is a function of x and y, then this just sort of leads to a default parameterization, where just it's a function in x and y. So you have some surface defined by z equals f of xy, and then it's x, y, and then the z component gets replaced with f of xy. So those are just a few examples. Now let's take a look at the exercises. So the first problem right here, identify the surface with the vector equation r of s and t equals s cosine t, s sine t, comma s. Okay, so what do you think? Now, if this wasn't an s here, let's say that was a 4 or something, a 4 cosine t, 4 sine t, comma s, then that would be a cylinder, right?
Yeah.
But since there's an s there, what do you think is going to happen? What happens when s is 0? But what you can do is you can, if you want, you can plot a few points and kind of see what goes on. So if you set s equal to 0, like I just choosing some values of s. Hold on a second. Oops. What you really have to do, actually, I got a bit ahead of myself there, is you have to give it s and t. So if you make both of those 0, then all these are right. Okay, so that's going to go through that point right here. What if you make? But then also it's kind of hard to figure out what's going on. And another thing you can do is if you set, let's say you set s equal to 1, for example, then what happens? Then what do we get? We have
Cosine t.
sine t,
Sine t.
and 1, I'm sorry. So that means your z is up at 1, right? And your x and y are cosine t, sine t. Now, what parameterization do you recognize that's like that? That's like cosine t, sine t.
Cylindrical.
Yeah, that's a circle, right? So it comes out of this 1. So that's going to be a circle like this. And then you maybe realize that as you increase s, then these circles are going to get bigger. Well, and you're going up and down. So the s is directly related to the z axis. So as you come up, you're going to get bigger and bigger circles. And then if you get big enough, then you're going to pour some water in there and drink it, right? Or maybe lemonade. Okay. If you go down, then it's going to be also going down. It's going to be weird too. The anti-cone down. So out of all the options, hold on. Which one do you, so if you got the homework open, which of the options best describes it?
Already tried number 2, it's wrong. So wait.
Okay, it's the circular cone. Circular cone. Okay, so the elliptic cone, well, I guess it is an elliptic cone too, but an elliptic cone would be, if I was to put like a 2 right there in front of it, so the 2s cosine t, just change, so these numbers are not the same, then that's going to be an elliptic cone. But it's not, so circular cone. It is. Okay, now, wow. Number 2, match the correct figure and determine families of grids with U constant and V constant. Oh dear. Okay, so now, so what we need to do is, first of all, we're going to go with this one, U constant. Okay, so imagine U being a constant, and maybe we can even set it equal to a value. Maybe, what if we set U equal to 1, for example, and in all of these equations? That is like really weird. Okay, so U, dang. Okay, so if we made U equal to, equal to 1, then we would have X would be 1 minus
1 minus 1. That's 0.
1 minus 3 minus cosine of 9d times cosine of 4 pi, and then cosine of 4 pi is going to be, it's going to be 1. Okay, so this is going to be -2 minus cosine of 9d, and then y is going to be, okay, that's weird. So y is 0. That turned really bad. Okay, and then z is going to be 3 plus 1 minus r sine d. Holy smokes, that's like really weird. Whoa. This is the weirdest thing. So this is x, that's v. Now, maybe we can choose a different value of u. Maybe we can choose u to be, okay, well, let's try to figure it out. So the options are a vertically oriented circle, a vertical plane, y equals tangent cubed of u, x, what? A circle of radius modulus of u in the horizontal plane. What? Okay, so it's not going to be in the horizontal plane because the horizontal plane would just be x and y, right? But this has a z component. And then the other option, each grid curve is a helix. Okay, this is not a helix. Okay, so a helix, so just so you know, a helix, that would be where you have like cosine, maybe r cosine theta, sine theta, and then theta. That's going to give you a helix if you have something like that. Oh, this is r sine theta. So it's not a helix. Each grid curve lies in a plane that includes the x-axis, the circle of radius in the horizontal plane. Okay, so it's not in the horizontal plane. Okay, so this is a vertically oriented circle. Okay, so don't spend too much time. You can guess around on these if you want. It's a vertically oriented circle. Okay, now the v constant. If we set v constant, what do we get? So let's choose some values for v. So what if we set v equal to 0. Okay, so that would give us x would be 1 minus u times 3 plus,
4 plus 1.
oh yeah, 3 plus 1, okay, times cosine of 4 pi u. And then, so that would be 1
4.
minus u. What the? Okay, y would be 1 minus u times
4.
4, right? And
Yeah.
that would be sine of 4 pi u. V would be, that'd be 0. So it would just be 3u. So, So we have this, and that. What the? Super. Okay, this is going to be a spiral curve. Because kind of like a helix, except you have constants out in the front here. Okay, but you have these two right here. So this means it's going to spiral around. Okay, so spiral curves. And vertically oriented circles. Okay, so which one of these is it going to be? A, B, C, D, E, or F?
E.
I'm gonna say E. Or that one.
It was the cornucopia. Ooh. All right. Have you seen that video on YouTube about the cornucopia? Put it in the cornucopia.
No.
Okay. That's okay. Don't watch it. Okay, so number 3.
Okay.
Okay, so here we're supposed to find an equation tangent to the plane at 2, 2, 2. And here we have the parametric equations of a surface, right? And so here, yeah, so this is kind of like, so basically what we have here is the x component is u plus v, the y component is 2u squared, and the z component is u minus v. I'm just pointing out that this is like that, okay? So this is sort of what we're doing. Okay, so we want to find the equation of the tangent plane at that at that point. And you want it's the point where 2, 2, 2. So this means that x is 2, y is 2, and z is 0. Okay, so to get this point, can you guys guess what values of u would get that to us? You can try guess some values of u, or we can try to solve it. Try to set u plus v equal to 2. Okay. Okay, so that would be u plus v equals 2, and this would be 2 u squared equals 2, and this would be u minus v equals 0.
It's 1. U and V
1 and
is
1. 1 and 1, right? So this first and last equation forces them to be 1 and 1, and then the middle one is just, we're really lucky that worked out. So 1 and 1. Okay. Now, okay, so what you're going to do is you're going to find 2 vectors at the point. And the first one's going to be RU. And the second vector is going to be RV. Okay, so first of all, are you? So basically what this means is you take the partial of each of these components, that one, and that one with respect to u. So if we take the partial with respect to u here, we're going to get 1, right? And then what do we get here? Partial of u of this.
For you.
Yes, for you. And then here we're going to get
1.
1, all right? Okay, and now partials with respect to v.
1, 0, and -1.
Okay, zeros are good. Zeros are our friend. Okay, so now what you're going to do is you're going to plug in 1, 1. So you're going to let u equal to 1 and v equal to 1. So you just get that. And then this is still the same, okay? This is still the same. So you would plug it in here, but it's just going to still be the same, like that. Okay, so these are 2 vectors that are tangent to the surface at this point. Okay, now to find the tangent plane, do you remember what vector is good to find the equation for a tangent plane? Does anybody remember that?
Oh, you can use the cross multiply.
Yes, exactly. So you're going to do the cross product because that will give you the normal vector to the plane. Okay, so good. So you're going to use the cross product to get the normal vector. Okay, so as is customary, I'll copy on the first 2 columns like that. Okay, so we have going down this way, we have -4i, and then we have plus j, and that's 0, so that's gone. And then going back, we have minus, and then you have 4k plus 0, and then minus j. Okay, so in the end, we're going to get -4i, and then you got j plus j, so that's 2j, and then you have minus 4k. Okay, so you have that, but then this is a multiple, so you can use, instead of doing that one, you can use, divide everything by 2. Divide by -2, I'm sorry, because I like to lead off with a positive. So 2i minus j plus 2k. So you can use that one. Okay, so equation of the tangent plane. Okay, that's going to be 2 times x minus the x point, which is 2. Okay, and then minus 1 times y
-2.
minus 2, yes. And then plus 2 times z
D
minus
0.
Okay, so that right there, that should give you the answer if you just put it in like that. Or if you want to, if you feel like simplifying it some more, then great. But this emphasizes the point. This form of the equation will emphasize that it's going to that point and it's the tangent at that point on the surface. Okay, so any questions about that? This is sort of what we've been going over before, right?
Yes, I think so.
Yeah. Okay. So number 4. So we're going to find the area of the part of the plane that lies in the first octant. So this plane right here that lies in the first octant. Huh. I forgot to copy down some formulas. Oh well. Okay, so now we're actually going to use, let me go back to here. And it is, so it's these formulas here. And you can use either the one on the left or the one on the right. Well, this is more general. This formula here is more general. So notice that it's the cross product of RU cross RV. It's the cross product of RU and RV, which we just did in the previous exercise. So that's really great. So this is if you have it in parametric forms. Now this one is if you have it like this. If you have it like that, z is equal to f of xy. Okay. And then this is if you don't have it and you don't have it like that, so you just use this one instead. Okay. So let's go ahead and tackle this one. Now, so we can, do you want to put it, you want to solve it, you can solve it for z. That's negative 4x minus 3y plus 12. So we can find zx and zy in this case. Okay, so what's zx? This is the partial. Yes, exactly. And zy would be
negative 3.
Negative 3. So that's the partial of this with respect to y, and this is the partial of this with respect to x. So you just get these coefficients here. Okay, now we need to know something about this plane. In the first octant. And so what happens is, if you look at it this way, then when x and y are both 0, then you're up here at 12. But then what's going to happen is it's going to come down and be something like that. So so you want to know what the area of the surface is right there. But what we need to look at is we need to figure out this piece right here down here in the XY plane, what that looks like. Okay, which we're going to try to simulate right here. Okay, so first of all, where do these intersect? Where do these intersect here and here?
That's gonna be 12 for y and 4. Is it just
So
gonna be the equation?
So what you need to do is set this equal to 0. So negative 4x minus 3y plus 12 equals 0, which is going to translate to 4x plus 3y equals 12. Okay, so when y is 0, so if you cover that up, what's x going to be?
3.
Yeah, that's going to be 3, right? And then if x is 0, then y will be 4. Okay, great. And then this line right here if you solve for, let's see here, you get -4/3 x plus 4, right?
Mm-hmm.
So you get that right there. Okay, so now we're ready to apply the formula. And it's the integral. And we can apply the, we'll call that d right here. 1 plus zx squared plus zy squared times dA, right? Okay. So if we want to integrate over this region D, then, and let's go y first and then x. What are the limits on y?
Gonna be from 0.
0 to 3.
Okay, 0 is the bottom one. Okay, now draw a vertical line segment. This is the bottom boundary. Here's the top boundary.
0 to 4.
Gonna 0 to the equation.
The equation.
-4 over 3x plus 4.
Okay, so -4/3 x plus 4. Good. 0 to the equation. Now, x goes from
0 to 3.
0 to 3. Okay, so x goes from 0 to 3. Okay, so imagine, okay, so when you're doing the first one, look at all these vertical lines of of varying heights. Okay, you have one here, one there. There's all throughout the whole region, right? So you're going from, and they all go from 0 up to here. That's how you can describe every single line, every single vertical line segment here. It goes from 0 to that in the y direction. That's its length. In other words, its length is this minus that. Okay, now when you go in the x direction, you had all these vertical lines, and if you wanted to add them all up, you can go from 0 to 3, and every point here gives you a vertical line segment. Okay, so this piece is going to be the square root of 1 plus, this is weird, so gx squared, so that's 16. And this one is 9. Whoa. Interesting. Okay. Which is, I'm going to pull that all the way out, actually.
Square root of 6.
Okay, so that's going to be the square root of 26. That's weird. Oh, well. Now, when you integrate this, you're going to get y, and then you're just going to like take it from 1 to there. So -4/3 x plus 4 dx. Okay, so integrating this, we get -4. No. 2 thirds x squared.
That's 4x.
Yeah. Okay, so from 0 to 3. Okay, so put a 3 in. Oh, good. Goody, goody, goody. So this is -6 plus 12 minus 0. Oh, yay. So 6 root 26. Okay, so 6 times the square root of 26. Yay. Okay, let me point out one thing really quickly. So we have one more exercise to go, which I guess we'll do tomorrow. But I want to point something out really quickly here. Okay, so that is back here, we use the second formula, right? We use the second formula. That's the one we used. We didn't use that one. But let me show you how what would happen if we use the other formula. Oops. Okay. So what you can do is you can write it as a parametric equation. Okay, so it would be x, y, and this one, negative 4x minus 3y plus 12. Okay, so this is what I told you. This is exactly this piece right here. This is how you parameterize if you have it. If you have the last one in terms of z, if you have z equals f of x and y, this is how you parameterize. Okay, and so now your x is kind of like this u. It's kind of like the u here. And so in general, you have u and v, but that doesn't really matter what variables you have. You just have one variable, and you have just two variables. Okay, here they're x and y. Here they're u and v. Okay, so and then in the formula they're u and v. But if you've got x and y, then they're x and y. Okay. So RU, so the next thing we want to calculate is RU and RV, or RX and RY would be what we're supposed to calculate here. So RX would be, so the partial with respect to x of all this is going to be 1, 0, negative 4, right? And the partial with respect to y is going to be 0,
1, and negative 3.
Perfect. Okay, so now the next thing in the formula called for was finding the cross product of Rx and Ry. So we go ahead and do that one. Okay, so that's going to give us 0. Ooh, I like that. 0, 0, and this is going to be
Okay.
Okay, and then minus, and then you have 0. Oh dear. Negative 4 I, and then
Negative
minus 3. Okay, so there's that. But what we're supposed to do is find the magnitude. Okay, so the formula says find the magnitude, and that's the square root of the k component, which is 1. No, I'm sorry. Let me write this out. This is 4i plus 3j plus k, right? Okay, so it is the I component, which is this one squared, so that's 16, plus the j component, which is squared, which is 9, plus the k component, which is 1. And that is, guess what that is?
26.
Square root of 26. So you get there, and then boom, it's pretty much the same as that. So if you work this way, then at that point you get the same thing. You get the same thing as we worked it this way. Except you just went through a lot more work, so maybe you feel good about that. Yeah, I went through more work. So, or maybe you're like, no, I went through more work, and the time that it took me to do that, I could have drawn a picture of something. Okay, but no. But instead, I spent all that time working this cross product thing. Okay, but then other times you have the surface, it's already parameterized, so then you have to go this way, right? So that's great. Okay. And then it says u equals 2, v equals 0. Okay, so did you start this problem at all? Did you start? What's that? You
Yeah.
don't know where to start.
Yeah, but
You know where to start?
I didn't really understand it, so.
Okay, so the okay, so here's the deal. The normal to this surface is going to be the cross product of the partials with respect to r and v. Okay, the partial derivatives of those. So, so you need to calculate, so RU cross RV, so that's what I need to calculate first. Okay, so if we put RU in, let's see, what's RU? Let's do it in red. So you take the partial of everything with respect to U. Okay, so this one will be
2U.
Yeah, 2U. And this is 9 sine V, and that one's cosine V, right? Okay. And then you do the partial with respect to V. Okay, and that's going to be, oh, yay, 0. Yay, that's good. Okay, then you have 9U cosine V. And what's this? Negative U sine V. Okay, so we have that. That's interesting. Okay. Okay, so copy that stuff down. And it's going to give us, in the I direction, it's going to be negative 9U sine squared V. And then going back the other way, it's minus 9U cosine squared V. Oh, that's nice. And then in the J direction, it's 0 minus this. So this is plus 2U squared sine V. And in the K direction, it's going to be this minus that. That's 0. This one is going to be 18U squared cosine V. That's interesting. Okay, so there's our, that's our cross product right there. Oh, except this simplifies down to, just negative 9U. Now, we're going to set U equal to 2 and V equal to 0, because this condition right here. Okay, so if U is 2, then we're going to have negative 18. And if V is 0, then that's going to be 0. And that's going to be 1, so that's going to be 2. 18 times 4, basically. So you can factor a negative 18 out, and you have 1, 0, negative 4.
Where did that 4 come from?
Here, setting U equal to 2.
Got it.
Okay, so essentially, though, you can just ignore this negative 18. It looks scary. I don't want to. I want to go hide under my bed. Ignore it. So just ignore it. Okay. And you're supposed to find the equation. So this is a normal vector to the curve at the corresponding point. Okay. So another thing that you need to do. Okay, that's the cross product evaluate. This is the cross product evaluated at this values. You need to evaluate this at these values also. So R of 2, 0. And so I'm putting a 2 in for U and a 0 in for V. So that's going to be 4. And then 0 for V makes that 0. Well, that's weird. And then this one is 2 there, and that's 1, so that's 2. Okay. So this right here is going to be a point on the plane. There's a point, and there's the normal vector. So the equation of the plane will be the dot product of the normal vector with x minus 4, y minus 0, z minus 2. Okay, so in other words, it's going to be 1 times x minus 4 plus 0 times y plus, or rather, minus 4 times z minus 2 equals 0. Okay, so x minus 4 minus 4 times z minus 2 equals 0. Weird. Let me see if that's the right answer. Yes, that's the right answer. So this will work. You can probably also simplify it and it would still work. Now for the second part, let me see here. For the second part, you have just an equation in which of those graphs does it look like? Well, it's going to be tangent somewhere, so it can't be the second one. The one on the top right, that's impossible to be that one. And then we have to figure out if we simplify this. So we know that it goes through that point right there, 4, 0, negative 2. We know that it touches the plane at that point. If we simplify this, let's see. We have x minus 4z plus 8 equals 0. Negative 4z equals negative x minus 4. Okay, so z is negative is 1/4 x plus 1 looks like. So if this were z and this were x, I mean that's kind of awkward, x and z, but whatever. Okay, then it's going to be something like this, like that. And then if we had y coming out towards us, no, y going into the computer or into the screen, then so this is going to be a plane, right? That's coming out towards us and also into the screen and beyond. And it's going to go to the point 402. So which one of these figures do you think it is?
The one that looks kind of like a shed roof.
Like a what?
Like cemented.
Wait, are you saying the bottom left?
Yeah, I don't know if it's the same for you, but the bottom left for mine.
Yeah, that's it. Because if you look at the point 402, so first of all, oh, that's weird. Oh yeah, so you want x to be 4, and that puts it at 4, and z to be 2, and then y to be 0. That's where it's going to intersect. Okay.
Thank you. That works.
Great. Any other questions? Okay, let's go ahead and finish up number 5 on the A homework. Okay. And let me come back here to the A homework. Okay, so we're supposed to find the area of the part of the surface that lies within the cylinder, x squared plus y squared equals 4. Okay, now remember, for the area, we have these two equations right here, that one, and then this one. If you have it as z equals something, then we use the second equation, which is what we have. We have z equals x, y. Okay, so we're going to integrate over. So this is a weird surface up, you know, and then it's within this cylinder, x squared plus y squared equals 4. Now, first of all, let's go with the first equation. So inside this integral, we're going to have to put 1 plus, maybe I'll write it out, zx squared plus zy squared dA. Okay, so what is, so the partial with respect to x, what is that?
Just y.
Yeah, that's y. So you got y squared here. Don't forget to square it. And then the partial with respect to y is just x. So you got x squared. And you have dA. Okay, now you're within this cylinder here. And so the cylinder is another story. In polar coordinates, okay, what's the radius of this?
2.
2. So in polar coordinates, you got r going from 0 to 2, and you have theta going from 0 to 2 pi, because there's no restriction on it going all the way around. Okay. So for r, it goes from 0 to 2, and theta goes from 0 to 2 pi. And this part right here, what do we change this to?
Polar coordinates?
This. Yeah. In particular that.
R sine.
Yeah, that's going to be.
Oh, never mind.
Yeah, x squared plus y squared is just r squared. So that's what you get there. And then the dA changes to r dr d theta. Okay. So I probably, instead of writing it this way, I'm going to go that way, because that's just easier for me to integrate. Now, like I said, I've said many times, there's no thetas in here. So this part's just going to give you 2 pi. Okay, and the other part, we'll integrate that. And that gives us 1 plus r squared to the 3 halves. So we raise that by 1. But then you have to have a 1/3 out in front, because you're going to have a 3 halves come down. The 3 gets knocked out there. And you'll have a 2 down here. But then the 2r comes out. With the r's there, and the 2 reduces with the other 2. Okay, and that's going from 0 to 2. Okay, so you have 2 pi over 3, and then we have, you putting in the 2 in, we get 5. So 5 to the 3 halves is 5 root 5. And then we put a 0 in, you just get 1. Okay, so this should be the answer right here. Okay, now I want to also show you that I also want to show you the other formula really quickly. And that is, instead of doing it this, instead of like having this, instead of that, we have, let me show you. So we did this one right here. So instead of that, we're going to look at this one now really quickly. Okay, this right here. So that means that you have to parameterize it somehow. And the best, well, you're parameterizing this right here. And so it says, you know, in general, it's U and V, but you can choose any variables that you want. And in this case, it's best to choose those two, X and Y, because X can just be itself, Y can be itself, and then Z becomes XY. So basically X takes the place of U and Y takes the role of V. Okay, so that's parameterizing this surface. And then our X is, so the partial of all this with respect to X, that's 1, 0, Y. And then our Y is 0, 1, X. And if you take the cross product, Rx cross Ry, then well, these are like not lined up very well at all. Wow. Okay, so you get negative yi minus xj plus k. And so then, but then what you're after is the magnitude of the cross product, which is the square root of this one. I'm going to go back. Well, I can go this order here. So y squared plus x squared. So it's the square of each of these. So that means you drop the negative signs. You get that. And the point is that this is the same as this. Okay, so you can go this route and come to that point, or you can just use this and go to that point, if you have this kind of situation. Okay, I just wanted to emphasize that again. Okay,